Hi everyone, and welcome to the introductory lecture of our first application, namely pneumonia classification. In the following lectures, you will learn how to build a classifier which is able to identify signs of pneumonia in X-ray images. Pneumonia is a common infectious disease that is responsible for over 1 million cases and tens of thousands of deaths annually in the US alone. As an example, in 2017, 1.3 million cases were reported, of which over 50,000 died, resulting in a death rate of nearly 4%. Therefore, and I am sure you will agree with me on that, it is absolutely crucial to recognize a pneumonia in time, as otherwise it can be life-threatening. To tackle this problem, we will use the RSNA Pneumonia Detection Challenge dataset provided by the Radiological Society of North America. It consists of 26,684 X-ray images, of which about 20,000 do not show signs of pneumonia and around 6,000 actually do show signs of pneumonia. As you can see, the data is quite imbalanced, which increases the challenge. In this example, you can see 4 X-ray images where the 2 pictures in the left column do not show any signs of pneumonia, whereas the patients in the right column actually suffer from pneumonia. Now, after getting to know the problem and why it matters, it is time to dive into the technical aspects. At first, we need to define our data pre-processing routine. The original X-ray image of the pneumonia detection dataset have a shape of 1024 by 1024. This is way too large for current machine learning algorithms, thus we resize all images to 224 squared. Next, we standardize all pixel values into the 0-1 interval by scaling them with a constant factor of 1 divided by 255. Or in other words, we multiply all pixels in all images with this constant. Now, after applying the pre-processing steps, we split the dataset into 24,000 train images and 2,684 validation images. This is crucial when tackling machine learning problems to make sure that your model is able to generalize to unseen data and not simply learns the label of all images by heart. Now we use a trick that allows us to leverage the Torch Vision dataset folder class by storing all processed images in specific folders. Images that do not show signs of pneumonia are stored in directory 0, and all images with pneumonia are stored in directory 1. Therefore, we have folders 0 and 1 in our train directory and folders 0 and 1 in our validation directory. Additionally, we compute mean and standard deviation of the training dataset for the purpose of normalization. However, the dataset is quite large and may not fit into the memory. Thus, we will use a little trick which allows us to still compute those 2 values. For each image in the dataset, we calculate the sum of the individual pixels as well as the sum of the squared pixels. Then we add those 2 sums to 2 global variables called sums and sums squared. We can now compute the mean by simply dividing the sums variable by the number of images in the dataset. In this case, this would be 24,000. Now we calculate the fraction between sums squared and n and subtract the squared mean from this expression. Subsequently, we take the square root of this result, which delivers us the standard deviation. Cool, isn't it? Instead of loading the whole dataset into the memory, we only need to update 2 sums to compute mean and standard deviation. Now it is time to create our dataset. As already said, we will make use of the Torch Vision dataset folder class, which alleviates the need for a custom dataset. When loading an image, we set normalize the image pixel values with our pre-computed mean and standard deviation. Set normalization is performed by subtracting the mean from all pixel values and subsequent division by standard deviation. Additionally, we apply random rotations, random translations, random scales, and random resized crops for the purpose of data augmentation. Or in other words, we randomly rotate images, we randomly scale images, we randomly shift images, or we randomly crop a portion of the image and then resize it to the original image size of 224 squared. To tackle the training, we use a library called PyTorch Lightning. PyTorch Lightning is a high-level PyTorch wrapper for simple and effective training that facilitates us some points. It alleviates the need of a manual implementation of the training loop. It automatically handles multi-GPU and comes with extensive logging and callback interfaces. Last but not least, and this is really the great point of PyTorch Lightning, you still have full and easy access to all internal variables and parameters. We use the famous ResNet 18 as our network architecture. However, as we are working with medical images, which are typically not in the RGB format, we need to change the number of input channels from 3 to 1. Additionally, as we only want to classify whether there are signs of pneumonia in an image, we change the output dimension from 1000 to 1. As loss function, we use the binary cross entropy with logits loss. This loss is directly applied to the logits, or in other words, the raw prediction values returned by your neural network. A negative output or a negative logit means that the network didn't see any signs of pneumonia in the corresponding image. In contrast, a positive output or logit means that the network saw some signs of pneumonia. We use the famous Adam optimizer with a learning rate of 1e-4 and then train the network for 30 epochs. After training and evaluating our model, let us take a quick look into the field of interpretability. Wouldn't it be cool if we could answer the question why our model outputs pneumonia for a certain image? If this would be possible, it would significantly increase the acceptance of such models in the general population and also amongst medical professionals. Luckily, this is in fact absolutely possible by extracting the image region with the largest influence on the prediction. Or in other words, we need to find out which part of the image supports the classifier the most in its prediction. One way to achieve this is to compute the class activation map as proposed by Su et al. In its paper Learning Deep Features for Discriminative Localization. The class activation map is computed in the following way. At first, we need to grab the output of the last convolutional layer. So instead of only storing the prediction, we also store the output of the last convolution in the network. Those values are called features. Next, we need to extract the weights W of the fully connected layer. Those are the weights responsible to transform the output of the last convolutional layer into the raw prediction of our network. Now we simply compute the dot product between our k feature vectors defined by A and our weights W. This produces the final class activation map. In Python, the computation of the class activation map M looks as follows. At first, we create an empty cam array which will take as many elements as the product between the width and the height of our feature matrix A. As an example, if your last convolutional layer outputs a tensor of dimension 24 times 7 times 7, Then the class activation map consists of 49 values. Now we loop over those 49 values and compute at first the product between our weights and the features at the corresponding index I. In our example of 24 filters, we have a weight vector that consists of 24 elements and 24 features at each of the 49 positions. Therefore, this multiplication consists of 24 elements, of which we take the sum subsequently. This result is then stored at the ith index of the class activation map array. You will also learn how to implement this methodology in the programming lecture of this section. When applying this procedure to an example of our X-ray classification dataset, it returns the following class activation map. In this example, we can see that the somehow noisy looking right part of the lung supports the classifier to output pneumonia. And in fact, this milk-like appearance is a pneumonia. Isn't that great? We just extracted the knowledge of our classifier to produce a heat map showing signs of pneumonia on the image. However, there are some restrictions when you apply the class activation map. At first, it only works with convolutional neural networks, and in fact, it needs a specific network architecture. Namely, the last convolution must be followed by a global average pooling layer, which is then followed by a single fully connected layer. When you want to apply class activation map based methods to other network architecture or a non-convolutional neural network, you can use some alternatives. As an example, GradCam and GradCam++, which are both extensions of the CAM method. Additionally, if you want to use a more recent method, you can also try ScoreCam. Now that we've gone through the motivation for a pneumonia classification model, the pre-processing of X-ray images, the creation of our classifier, and even an introduction to interpretability, it is really time to get our hands dirty and code all of these things. Thank you and happy coding!